All right, advanced placement calculus. Let's get rocking and rolling. Another, advanced placement calculus virtual review lesson. So today is Tuesday, the 28th, I think. Okay, your AP is in 2 weeks. Okay, 2 weeks from today. Make sure you check my website. Okay, you guys got to log into my AP on the College Board website. And then you could review your cell phone number and your email that the College Board has on file for you. Because when you take your advanced placement exam 2 days before, they're supposed to email you a little e-ticket so you can get into the exam. That's important. I don't want you stressing about these things on the day of the exam. Let's make sure we take care of these things, a little bit earlier. You'd have to upload your answers on the AP exam. I don't know if you got to upload them in PDF. You might be able to just take a picture and send them in. But these are things I'll look into, and you want to look into as well. They're going to email you stuff so that you're ready to actually take the AP exam. More on that is going to be released this week, I believe. They're going to have a little checklist for you guys to go through. Anyway, let's get rocking and rolling. Okay, a new little topic that we're dealing with. The last thing we dealt with was what was it? Differential equations? I think it was differential equations. Okay, technically now, we're going to talk about a packet that I like to call tables, okay? But it's also miscellaneous. This is kind of the other types of problems that are left over. A little bit different for you in the AP this year. I always try to predict problems. It's different because I don't know what the heck they're going to come out with this year, but I at least have, my mind thinking about it. In previous years, though, table problems very popular. Maybe not necessarily something like the 2014 problem, even though you will probably see stuff like this. The one after it, a little bit more, traditional as far as the AP exam is concerned. But this problem right here, 2014, no calculator. Lots of tables going on. They talk about the twice differentiable function f and g. Okay, so you could take two derivatives of those are defined for all real numbers x. Then they tell you values of f and g and their derivatives are given in the table above. So we got functions represented tably. Just be careful because you don't really know what's happening in between these intervals and in between these numbers. Well, I guess you do. Here you got -1 and 1. They tell you about the functions and they tell you about what's going on in between. They did tell you the functions are twice differentiable. So they're continuous everywhere, differentiable everywhere. No funny business going on here. And part A, which is part A, we want to find the x-coordinate of each relative minimum of f on the interval -2 to 3, the closed interval. Justify your answers. It's actually interesting. They usually never ask you about relative extrema at a closed interval. So I'm going to bet that there's not an extrema. Bet at -2 or 3. Even so, they don't tell you the function is only defined from -2 to 3. They tell you all these functions are actually defined for all real numbers. Okay, so technically -2 and 3 aren't endpoints. I don't think they're going to come into play here. We'll see. If you want to find a minimum, well, surely there must be some sort of test, okay? And we know it's the first derivative test, and we know f is the OG function. So you want to take the derivative of f. We want to draw the f prime line. Is it bounded? It is from -2 to 3. Oh, sorry. That's where I draw the line. The f prime line, okay, bounded from -2 to 3 right here. And then, look, you want to put all critical x values on the f prime line. Where's f prime equal to 0? We know it's equal to 0 at -1 and 1. Okay, now we just want to plug in values in between to f prime. So, -2. Oh, you don't even have to plug the values in. They tell you f prime from -2 to -1 is going to be negative. Put a little negative sign right here. F prime from -1 to 1 is negative again. And then from 1 to 3, f prime is going to be positive. Okay, and we also know that we got our little horizontal tangent lines here because that's where f prime is equal to 0. So the graph of the function f would have that horizontal tangent line. At -1, no extrema. You got the decrease and the decreasing thing going on. If -2 is an endpoint, it would actually be a maximum, just like 3 would be a maximum. So once again, they never really ask about relative extrema at endpoints, but 1 looks like the min right there, okay? So the x-coordinate of each relative min, so rel min, or local min, you could say that. We'll say at x equals, 1? Because got to justify your answer. We've been doing a lot with this, okay? Justify in terms of the function you're given. They tell you about f prime right here when it's positive or negative. So we know right here that first, make sure you put f prime equal to 0. Some people leaving that out. Some of the assignments I've been grading. Those assignments, I will have the answer keys posted, okay, a decent amount of time so you can actually check your work and see where you went wrong as far as points are concerned. Also, I believe I'm assigning another assignment tonight that's going to be due on Friday. Sorry for so many assignments, but I got to make sure that people are actually doing work, okay, and ready for the AP exam. Not just because f prime equals 0, by the way, because f prime equals 0 and changes, we know from negative to positive. From negative to positive. Okay, so hopefully not a terrible problem right there. Part B might actually be the toughest part of this problem right here. That happens a lot. So if you see a part B you can't do, don't be like, well, there's no way I'm going to do part C. No, do the best you can, okay? Move on if you want to. C and D, as nasty as they seem, they're actually not that bad. Explain why there must be a value C from -1 to 1 such that f double prime of C is equal to 0. You don't see this a lot. Sometimes they just want a y value to be equal to something, like maybe they say f of c equals 0. That's an intermediate value theorem problem. If a function's continuous, it's got to take on all y values from one y value to the next y value, to another y value. Sometimes they force a derivative equal to something. If they just said f prime of c equals 0, then I would have you think in mean value theorem when they tell you derivative has to equal something. This is a second derivative equal to something, but believe it or not, it is the mean value theorem, and people get annoyed. They're like, wait, how is this the mean value theorem? The mean value theorem is when f prime of c is equal to, some value. Well, the function f, they tell you, is twice differentiable. That means his second derivative exists. So if f double prime exists, that actually means that f prime is differentiable. I'm going to say if, you don't need to write this, but I'm writing this for you. If f double prime exists, that's the derivative of f, okay? So that means, that's the derivative of f prime. So that means f prime is differentiable. And if f prime is differentiable, we also know that it's continuous, also continuous. All right, so if a function is continuous and differentiable, it's got to satisfy the mean value theorem. There's got to be some place where the slope of the function is equal to the instantaneous slope of the function is equal to the average slope of a function, right? Where the instantaneous rate of change is equal to the average rate of change. The problem is we're going to perform the mean value theorem not on f. We're going to perform the mean value theorem on f prime. So you want to say that the slope of a line tangent to f prime at x equals c, that's f double prime of c, is equal to the slope of a secant line on the graph of f prime, not on the graph of f. And that's really difficult to see. You really kind of just used f prime for the mean value theorem instead of using f. So once again, if that confuses you, try not to freak out about it too much. But you also want to find out a place where this equals 0. So to find out where a rate of change is going to be equal to 0, you might want to say by the mean value theorem, you got to say something about because f prime is, I'm going to say continuous and differentiable. If you just put differentiable, I think you're going to be okay. But once again, if you're going to apply the mean value theorem, they want that written down. We kind of had it over here, but maybe this is where you start in the problem. We want this to equal 0, so you just want to find a place where f prime of b equals f prime of a. And take a look at f prime. You can see that x equals -1 and x equals 1. You get a y value of 0 back. So if you actually set this up, f double prime of c, and you use b being equal to 1, so f prime of 1 minus a being equal to -1. And then down here, you wouldn't have b minus a anymore. Now you would have 1 minus -1. Now you're going to get that f double prime of c is equal to 0, okay? So explain why there must be a y value, an x value c, such that f double prime of c is equal to 0. Because f double prime exists, that means that f prime is differentiable, which means it's continuous, and that means that we can actually use the mean value theorem on f prime. It's actually Rolle's theorem used on f prime. You might be chalking up b as an L, so please don't let stuff like that bother you. I know your AP exam, by the way, it's only going to have 2 questions on it. I'm thinking one is going to be your normal length right here, and another one, because it says average 15 minutes, you're supposed to have about 15 minutes for each problem. The other one's going to be 25 minutes, so I'm thinking a bigger type of problem, maybe some short answer in there and stuff like that. So if you encounter a part of a problem you don't know how to do, move on from it, okay? Maybe you read it, you're like, what? Immediately, move on. Don't let it ruin you. And C is actually not bad. We've done this a lot. A lot of people are horrible at this on the AP. Hopefully you're not too terrible. They give you a nice little composite function here for h, a partially abstract. H of x is ln of f of x. They want h prime of 3, the derivative, show the computations that lead to your answer. Well, if h prime of x is equal to, what do we got? Ln of f of x. You should know how to, that's what h of x is equal to. You should know how to take the derivative of an ln. Remember, the derivative of ln u, 1 over u times the derivative of u. You could already see the argument of ln is not one single x here, which means you need to use the chain rule. Just remember, if you take the derivative of ln anything, you get 1 over that thing, right? The derivative ln x is 1 over x. The derivative ln f of x is 1 over f of x. But now you got to say, whoa, hold on a second. I just took the derivative function. The argument is not one single x. Got to multiply by the derivative of that argument afterward. A lot of people struggle with that on the AP exam. We've talked about it a lot, so you should be better at that than most people, but this is why we do review. By the way, h prime of 3, let's plug all this stuff in here. Replace x with 3. All right, so really this is just giving me 1 over f of 3. If I look at my chart, f of 3 gives me 7, so that's luscious right there. 1/7 times f prime of 3, which we know is actually f prime of 3 equal to what, 1/2? All right, so you could leave it as 1/7 times 1/2. You could put 1/14 in there if you want to. Your AP exam is going to be all, free response. So you're not going to have to simplify anything, which should be useful. But once again, you'll have the calculator right next to you anyway. You're supposed to do this problem without a calculator, but they're not going to be able to give you problems that you can't use a calculator on because you'll have it in front of you. But they're saying that you won't really need the calculator, but keep it close by anyway. I'm also going to print up a little formula sheet for you guys. Okay, I'll get that on the, I'm not going to print it up. Hopefully you'll print it up. I'll get that on the website at some point in time. And then you could have that with you as well. Even though I'm not really a big person with formula sheets. Some people like them. I don't think they're as useful as some people might think. But if you like that, I'll have that for you. And then, part D, this is 2014 right here. Okay, it's 6 years ago, but it feels like recent to me because I remember this problem, and students, after I saw it, we were having a conversation about it, and I'm like, wow, an abstract integral? Like abstract derivatives on the AP all the ding-dong day, but an abstract integral, this is cool. The first one I had ever actually seen, and really, it's not too difficult. Like people look at it, they're like, not too difficult. Look at this, it's hieroglyphics. This is crazy here. Remember, if you want to integrate, in this class, there's only really one integration technique you use, and that's U substitution. Unless you could actually turn something into basic integration by algebraically manipulating it, you can't algebraic manipulate this. I mean, it's abstract. You don't even know what these functions are. And you can see that f prime, his argument is not one single x. There's also multiplication going on. This is a prime U substitution situation. And I get it, it's not so easy to pick a u, but remember, we use u so we could force the argument of a function to be one single letter, so we could actually integrate it. And you can see the argument of f prime is g of x. If you set u equal to g of x, look how amazing this is going to be. Remember, it's du over the derivative of u is equal to dx, and the derivative of g of x, that's g prime of x, and that's going to be generated downstairs. That's going to wipe out this g prime of x right here. So first off, don't forget, U substitution with the definite integral, tres substituciones. You need to actually change the bounds as well. And if you do change the bounds, it's not bad. Like g of -2, for -2, when x is -2, what the heck is u equal to? Well, u is equal to g of x. So that means if x is equal to -2, u is equal to g of -2. Look up here, g of -2 they give you is equal to -1, all right? So it's not really bad to change that bound. Just like here, the upper bound is 3. So if x is 3, what is u equal to? Well, u would be equal to g of 3. And if you take a look gander, up here, you'll see that g of 3 is equal to 1. So changing the bounds, really not too terrible. Now we leave that f prime, but it's f prime of u times the g prime of x is still there, but not for long, all right? Because I'm going to replace the dx with the du over g prime of x. So these guys are actually going to wipe out. And look how easy this problem has become, okay? Really, it's just become now the integral from -1 to 1 of f prime of u with respect to u. It's extremely easy to integrate. That's somebody's derivative in there. Whose derivative? The answer's derivative. You integrate f prime of u, you get f of u back. Pardon my language, evaluate it from -1 to 1. So what is that? F of 1 minus f of -1. And you can go right up to the chart. I could see that f of 1 is 2 minus f of -1, which is 8. And you could even stick it to the squirrels, baby. 2 minus 8. I don't feel like writing -6. It's actually not a terrible problem, okay? I had students this year on the AP exam. It was an interesting group of seniors. Kind of reminds me of you guys a little bit. But man, they came back and they were like, Berto, that problem was fun. They had fun doing it, okay? Very doable problem. Actually, part B, filth, okay? But besides part B, it's not really bad. Part A, you only get 1.4, but everybody should be able to get that. Don't screw up the justification. Part B was 2 points, and then these guys were 3. I mean, right there, nice 6 points, and then you could have a 7th point right there. Doing well, okay? So that type of problem right there, could see something like that in the AP exam. Let's jump ahead to 2012, okay? A calculator problem right here. This is a more traditional type of tables problem. You usually see problems like this on the AP every single year. Sometimes with calc, sometimes without. So you could see something like that this year. Not really worried about predicting too much yet. Let's just do our basic review first. Then next week we'll get into that. This is the last part of the part 2 review. Tomorrow, Wednesday, Thursday, and Friday, you guys will be working on another part 1. Okay, you can split up the work however you want over those 3 days. I'll post the videos for the non-calculator and the calculator part. And then next week we'll kind of try to get a little bit more topic specific, try to do some predictions and just some random problem stuff like that. So the temperature of water in a tub at time t is modeled by a strictly increasing twice differentiable function W, where W of t is measured in degrees Fahrenheit and t is measured in minutes. Okay, so at time t equals 0, the temperature of the water is 55 degrees Fahrenheit. The water is heated for 30 minutes, beginning at time t equals 0. So you can see up here in the chart, values of Wt is selected times of t for the first 20 minutes, given in the table above. So you can see from t equals 0 to t equals 20, this thing is being heated up, okay, the temperature of the water in the tub. And they also tell you what that initial temperature is equal to. It's in the chart as well, okay, so we can see a function right here represented table E. Use the data in the table to estimate W prime of 12. Show the computations that lead to your answer, and you want to use the correct units. Interpret your meaning of your answer in the context of this problem. So besides actually approximating a derivative here, sometimes they want you to evaluate a derivative here, they want you to approximate it. Then you have to actually explain what it means in context of the problem. You can still be pretty generic with that. But come on, this is an instantaneous rate of change, and there's only one way to approximate instantaneous rate of change. That's using average rate of change, and it's so popular on the AP. It would not surprise me if we see something like this. T equals 12 would be in between 9 and 15. 3 to the right of 9, 3 to the left of 15. That's where t equals 12 would be. So remember, we try to go a little bit to the left and a little bit to the right. So I'm going to say W15 minus W of 9 over 15 minus 9. Technically, you could use W of 12 for one of these if they gave it to you. You could use the point of tangency. You don't often see that, believe it or not, in the AP. Usually you move a little bit to the left and a little bit to the right. So you can see here now, if you just want to plug in W15, 67.9, minus W of 9, 61.8. And I'll even leave it over 15 minus 9. Stick it to the squirrels, baby, okay? That's the answer right there. If you want to get that as 61 over... Why do I have 61 over 60? Okay, so I guess it's 6.1 over 6. That makes sense. And 61 over 60. Anyway, you don't need to do that, but you do need units here, okay? And remember, W is measured in degrees Fahrenheit. But you just took the derivative of W with respect to T, right? W prime of T. So that's degrees Fahrenheit per T. So degrees Fahrenheit per minute. Okay, remember, it's the rate of change of the water temperature, right? That's what we're going to write up in a second. Degrees Fahrenheit per minute. Technically, actually, you could put that right there. There's nothing wrong with that. I probably have that on my answer key. I like to do that. But now when we actually explain what this means, I'll put the units in the explanation. It doesn't matter whatever way you want to do it. Just remember, this isn't a definite integral. We'll see in the next step, there's actually a definite integral that you have to explain, okay? Whenever you explain a definite integral, it's always the change in something, okay? The displacement, the actual change. When you describe a derivative, that's the rate of change of something. And we saw this before in AP review. The second you want to describe what a derivative represents, you write rate of change of. And then you stop for a second. You're like, oh yeah, what the heck did I take the derivative of? I took the derivative of W of T, and W of T represents the temperature in the water of the tub. So the rate of change of temp of water in tub, temp of water in tub. And then look, you want to say the units in, and we know it's degrees Fahrenheit per minute from before. But don't forget to describe units for the answer and a unit for that time T. I'm going to say at T equals 12, and then those units, minutes right there. That's important, okay? Just like an integral, you're going to have to use units for the answer and units for the bounds. Here, for describing a derivative, units for the answers and units for that t value. It's really at the rate of change of the temperature of the water in the tub at the end of the 12th minute, okay? And you can actually see it's actually positive, so it's actually telling you that the temperature is still increasing at the end of the 12th minute. But you don't have to write things in context that way. You could write it this way. It's still technically in context. You can get away with it. Part B. Now we want to use the data in the table to evaluate this integral, the integral from 0 to 20 of W prime of T with respect to T. And then we want to explain the meaning, okay? This is a joke, this integral right here. You don't even have to use a Riemann sum or anything like that. If you did, they would tell you. We'll get to more of that soon enough, okay? I think it's going to happen in this problem. Maybe not a Riemann sum, maybe a trapezoidal sum. I think this one's Riemann sum. Riemann sum. Anyway, so here, look, people are like, well, how do I integrate w prime of t? Well, that's somebody's derivative in there. Whose derivative? W's derivative. So wt, just like the last problem we did from 0 to 20, people are like, well, how am I supposed to know what values of w are? Hello, they're right here. So this really just becomes w of 20 minus w of 0. Whoa. Okay, and that's going to be equal to w of 20 is 71.0, so that's Mr. Harrington's age, minus w of 0, which is 55.0. It's Mr. Pushy's age. Okay, I'm going to circle it right there. I'm not going to do any subtraction. Okay, if you want to actually subtract it, be my guest and get your 16. What does this mean? Okay, well, first off, what did we just integrate? Okay, we integrated the function w prime of t. Well, w prime of t, think about it. That's the derivative of the temperature of water in the tub. That's the rate of change of the temperature and water in the tub. And if you integrate the rate at which the temperature of the water changes, you'll actually get the change in the temperature of water, which should make sense. I mean, it's straight up what's happening here. You're getting the change in the water temperature from t equals 0 to t equals 20 by doing that 71 minus 55. The water temperature went up by 16 units, 16 degrees. You could say that, or you could just say the change in temp of water in tub, change in temp of water in tub. Now you got to put in units, okay? So in degrees Fahrenheit, right? If you integrate degrees Fahrenheit per minute, with respect to minutes, you're going to get degrees Fahrenheit back, okay? In degrees Fahrenheit. And then we got to say the units, okay? So from t equals 0 to t equals 20, and that's going to be minutes right there. So here, a lot of times, you have to approximate the answer so you don't straight up get like this w 20 minus w of 0. But you can really see what's going on with the definite integral. If you integrate the rate at which the temperature of water in the tub changes, you get the actual change in the water temperature. That's what's going on there. So what does it mean? It means the water temperature went up by 16 degrees, but you don't need to say it that way, okay? So hopefully not too terrible, that part right there. Part C. Average value won't be on your AP exam, but they're actually talking about the average temperature of the water in the tub. If you want the average temperature of the water in the tub from t equals 0 to t equals 20, and you got a function that represents the temperature of the water in the tub, use the average value formula on that temperature. So you're not going to have to worry about it, but in past APs, I've told students, if they want you to describe the meaning of a definite integral with a fraction in front, then you want to say average value, okay? Here they gave it to you anyway, but now they want you to use the left Riemann sum with the 4 subintervals indicated by the data in the table to approximate this integral. Then they want to know if it's an approximation is an overestimate or an underestimate of the average temperature of the water. So let's get rocking and rolling. Here we have 1 over 20 integral from 0 to 20 of wt with respect to t. All right, so we want to approximate this, and I feel like I should move it down here. Let's do this because I want to make sure I have enough room to expand this. Who knows how long the expansion is going to be? All right, and I want to expand this using a left Riemann sum with the 4 subintervals indicated by the data in the table. So remember, if it was a Riemann sum where you had, using 4 subintervals of equal length, if they said it that way, then you get your delta t and you put it in front first. This is different. Okay, the 4 subintervals indicated by the data in the table from 0 to 20. We got to go from 0 to 4, then from 4 to 9, then from 9 to 15, then from 15 to 20. And we want to get the area of 4 different rectangles, okay? And the rectangle is going to be base times a height. So the first rectangle goes from 0 to 4, so I know the base is 4, right? You can imagine the first rectangle looking like this, going from 0 to 4. I know the base is going to be 4 right there, so I'm going to put 4 times. To get the height, okay, whatever the heck this function looks like, I don't know. Okay, to get the height, since it's a left Riemann sum, I want to plug in that leftmost x value, or t value in this case, to this function, so that's w of 0. And that right there is the area of the first rectangle. The second rectangle goes from 4 to 9, so his base is 5. But since it starts at 4 and ends at 9, since it's a left Riemann sum, I want to use the 57.1. I want to use w of 4 to represent the height. So w of 4 over here. Plus, we got that next rectangle, and that one goes from 9 to 15, so that's a base of 6. All right, w of 9, since it's a left Riemann sum. And then plus the last one goes from 15 to 20, so a base of 5, and then w of 15 to actually give us that right there. You don't need to simplify anything, okay, but what you should do is you should actually put this in numbers, okay? So 4 times, they like to see the expansion. They do like to see this. W0 is 55. Speed limit that I can't drive. Just kidding, it's a song. Anyway, so W4, 57.1. All right, plus 6 times W of 9. What is that, 61.8? Had a dog named 61 Point. I fed him 61.8. Here, boy. Plus 5 times W of 15, 67.9. Okay, and this right here, you could even box in. Okay, that right there, that's my approximation, okay, you know, which becomes 60.79 if you want to do that. You have a calculator, but you don't need to simplify it. Now, they actually want to know if it's an underestimate or an overestimate of the average temperature of the water. You know, remember, when you evaluate, oh, I messed something up here, by the way. It's supposed to be a 1 over 20 in front, right? Because we're actually getting the average. So technically, this right here is going to be 1 over 20 times this entire expansion. My apologies for that. It's a pillow parenthesis right there. Parenthesis, another parenthesis, little 1 over 20. So easy to do, by the way. You can see the mistake I almost made, right? You know, you just kind of worry about the definite integral. You kind of forget about that number in front, okay? So be careful. That does need to be there. And, you know, they want to know if a Riemann sum is an underestimate or an overestimate. Remember, that's about increasing and decreasing. You know, if a function is strictly increasing, you know, and you make a little left Riemann sum, okay, left Riemann sum, it's just such a terrible diagram right there. Let's do this, okay? Maybe the function looks like this. Get a couple subintervals going, right? 1, 2, 3 rectangles. Left Riemann sum, you want to use this guy to determine the height. So there's the first rectangle right here. Left Riemann sum, this guy determines the height. Left Riemann sum, this guy determines the height. So you can see a left Riemann sum, if a function's increasing, we have a lower sum. Okay, we have an underestimate. If a function's decreasing, some people have these memorized, by the way, okay? I don't like to memorize them because there's only so much you can keep in your brain. You could easily just model this out. You know, here, if it's a left sum and the function's decreasing, we plug in this guy to determine the height. Right here, plug in this guy. You'll see you're above the curve. And right here, plug in this guy. You'll see you're above the curve. So this function, W of t, if you go back all the way to the top, hidden information, they told you it was strictly increasing. Remember, if a function is increasing and you use the left sum, you get a lower sum. You get an underestimate, okay? So we know that this guy right here is going to be an underestimate, and that's because W of t is increasing. Okay, so be careful with something like that. I mean, it's not something you see a whole heck of a lot. Who knows if it'll show up for you or not. I'm sure you'll have some kind of Riemann something, but really it's not too terrible. Remember, you know, left sum, underestimate, increasing, overestimate if a function's decreasing. That's reversed for right sum. Right sum is an overestimate if a function's increasing and an underestimate if a function is decreasing. Trapezoidal sum, remember, trapezoidal sum is an over approximation, an overestimate if a function's concave up. And it's an underestimate if a function's concave down. Okay, things that we spoke about. I even wrote that down in the first multiple choice we went over. Don't know if you watched that video or not. You should have. Moving on to part D. For t equals 20 and t equals 25, this is crazy because it's outside our interval right here. So believe it or not, this tub exists after 20 minutes. That's kind of crazy. The function W that models the water temperature, which we never got. They just gave us, you know, points on that function, didn't tell us the function. Now they tell us the derivative of the function, W prime of t. Based on the model, we want to know the temperature of the water at t equals 25. Well, think about it. If you want to know the temperature of water at t equals 25, as long as you know some kind of initial condition, the temperature of the water at some other t value, and the rate at which the water is changing, you can get the temperature of the water at any t value. But this one's actually a little bit more confusing than you might think. We want W of 25. You can't start with W of 0. They tell you this W prime of t only exists from 20 to 25. So that means you have to start with W of 20, okay, which kind of bothers some people because, like, why do I have to start with W of 20? They gave me an initial condition, you know, t equals 0, W is 55. These are actually all initial conditions, okay? They're all points on the function, and here's the 21. They told you W of 20. Remember, I want to add to that, what the heck was the change in the water temperature, which means we integrate the rate at which the water temperature is changing, in this case, starting from t equals 20, ending at t equals 25. So this is the way to do it right here. It's really the only part that the calculator is necessary for. So 71 plus the integral from 20 to 25 of W prime of t with respect to t. Okay, so time for some calculator glory right here. good old calc. Okay, make sure once again, it's not going to matter. It is going to matter here actually because we got trig. Make sure you're in radian mode, always on the AP exam, radian mode. Technically, you're not supposed to even have to use the calculator. Like I said, 500 times for the AP exam this year. But if you do have your calculator with you, which you should, just in case, make sure you're in radian mode. Make sure you put the function in correctly, right? 0.4 radical t cosine of 0.06 t. Okay, so I have it right there. Okay, so now I got 71 plus a little, math niner? Nothing could be finer. Integral from 20 up to 25 of alpha twaithy, y1 with respect to x. And I get approximately 73.043. And remember, they said, what's the temperature of the water? So you could say degrees Fahrenheit. Technically, if you don't have the units, well, I guess you should. They say temperature. They never say in degrees Fahrenheit. So make sure you have that temperature as well. Not really too terrible, but definitely not a problem that's like a 9 out of 9, like some other problems that we did. Part A should actually be pretty easy for you. Part B is pretty easy as well. It was worth 2 points as well. That shouldn't be too terrible. Part C, even that shouldn't be too horrible either, but you can make some silly mistakes. That was 3 points. And part D, where the main problem is that people start with W0 instead of W20. That was 2 points right there. All in all, not the worst thing in the world. Try your homework tonight. I hope you've been working. If you haven't been working, it's not going to end well for you on this AP exam. It's going to be a horror. I don't care how well you've been doing in class all year. If you're slacking off, you will not do well. If you put in work, you could do so much better than you even did in class all year. You'd be surprised. Search your feelings. You know it to be true. Thank you, Mr. Vader. Anyway, that ends the section 2 review. We'll be jumping into a part 1, tomorrow, like I said, Wednesday, Thursday, and Friday. And then next week, we're going to rock and roll with more stuff. Try to predict some stuff, do some, problems. You'll still have AP review assignments. Make sure you're getting them to me. And until tomorrow, see you later, folks. Adios.